Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of electronic circuit. Today we are discussing the optical resonator. We are discussing the principles of optical resonator. Basically, the fundamental principle of the optical resonator is the resonance, and this phenomena where the light waves interact constructively within a confined space, leading to an amplification of the light intensity. So, there are the various points. First is the light wave and interference, another was the role of mirrors in the optical resonator, third was the formation of the standing waves which are required for the resonance, and another is the resonant frequency and modes. Optical resonators support multiple resonant frequency, that is called the modes, and these modes correspond to the different wavelengths that can form the standing wave within the cavity, and the mode structure depend upon the resonator's geometry and its mirror properties, mirrors arrangement and the cavity length. And in many applications, it is desirable to operate the resonator in a single mode so that we can achieve the controlled output wavelength. Another type of point in the principle of the optical resonator is the quality factor. So, the Q factor, that is the quality factor, is a measure of an optical resonator's ability to store the energy and maintain the resonance. So, a higher Q factor indicates lower losses and a more efficient resonator. So, whenever we construct any resonator, so first requirement is the higher Q factor, so that the losses will be minimum and the more efficient resonator we will get. So, the Q factor is influenced by the factors such as the mirror reflectivity, absorption and the scattering within the resonator. In a certain applications such as precision metrology and sensing, high Q factor resonators are essential for achieving the desired phenomena. Another important point is the gain and amplification. That's what we are doing. Construction in the resonator, we get the higher gain and higher amplification so that we can get the higher intensity of the light. In the certain optical resonators, basically if we talk about the lasers, so gain medium is introduced to provide the amplification of the light waves. So, the gain medium when stimulated emits the photons that are coherent with the circulating light. Means we must have a coherent light waves which is moving inside the cavity. So that it is bounced back, but it is in the phase, so that we can get the correct resonant frequency, and this process leads to the amplification of the resonant wavelength and enables the resonator to produce a high intensity output. By leveraging these principles, optical resonators can manipulate and amplify the light waves in a controlled manner, enabling a wide range of application in the modern technology. So, keeping in these points in mind, we can construct a resonator and we can further use for the modern technology applications. Now, we discuss the types of optical resonator. There are the various types, as we have discussed, that the Fabry-Perot resonator, and how we constructed we will discuss further in detail, but here we discuss the various type of the optical resonator. First is the Fabry-Perot resonator, and these are formed by the two parallel mirrors that create a standing wave pattern for light within this space between them. Means light is moving in these two parallel mirrors and it will form the standing wave. Another is the ring resonator, which light circulates within a cross loop. So, in a cross loop we can get light, and it is a ring resonator. Typically a waveguide or a micro toroid and can be used for sensing and filtering application. Another type is the whispering gallery mode resonator, and this uses the principle of total internal reflection within a spherical or toroidal geometry to trap the light. Basically, it is used in the fiber optics, enhancing its interaction with the surface. Another type of resonator is a spherical and hemispherical resonator, and these use curved mirror to focus the light and create the stable and unstable cavities depending on the mirror curvature and the separation. Means these mirror are stable or unstable have cavities are there in the spherical and hemispherical resonator. And there are another type also like the photonic crystal resonator. Nowadays we use for the these photonic crystal resonator for the Wi-Fi to send the internet and in IoT applications, and these use a periodic structure of the alternating reflecting indices to confine light within the specific region and creating the resonant mode. Another is a distributed feedback resonator, that is DFB, and these use periodic variations in the waveguide material to induce feedback enabling laser oscillations or the filtering. These use periodic variation in the waveguide material to induce feedback enabling laser oscillation or the filtering. What are the characteristics of the resonator? As there is a requirement of the stable waveguide inside a resonator, so first characteristic is the stability. Resonators can be stable or unstable depending upon the curvature of the mirrors and their separation. Stable resonators allow the light to circulate and oscillate, while unstable resonators are used for different applications like producing highly focused beam. So, another type of characteristics is the modes. Resonators support the different modes as we have discussed, longitudinal as well as the transverse. In the longitudinal we have different frequency, in the transverse we have different intensity patterns. Another is the resonator inevitably have some losses. So, another point is the losses such as diffraction and absorption, which can reduce the lifetime of the light within the resonator. So, in essence the choice of the resonator type depends on the specific application, whether it is generating laser light, sensing charges in the optical properties or performing optical filtering. So, now we discuss the various types of resonator in detail. So, optical resonator come in various forms, each with its unique characteristics and applications. Some of the most common type we have discussed: Fabry-Perot, spherical and cylindrical resonator, while more advanced resonator designs like whispering gallery mode resonator, photonic crystal resonator had emerged nowadays. So, first we discuss the Fabry-Perot resonator, and this type of resonator consists of the two parallel mirrors and forming a cavity where the light bounces back and forth, and this resonators type allow for precise wavelength control due to the ability to selectivity enhance specific wavelength that satisfy the resonance condition. So, this type of resonator are widely used in the spectroscopy, lasers, telecommunication system and wavelength filtering and stabilization. So, resonators, it allows a wavelength control due to the ability of selectively enhance specific wavelength that satisfy the resonance conditions. So, the Fabry-Perot interferometer is a linear optical resonator which consists of two highly reflected mirrors and is often used as a high resolution optical spectrometer. So, one exploits the fact that the transmission through such a resonator exhibits the sharp resonance and is very small between those. What is the operation principle of the Fabry-Perot interferometer? Fabry-Perot, we can say it is an interferometer and is a resonator. So, the following we are having a lossless symmetric high fineness and help to understand its operation principle. So we can have the substantial circulating optical power in the resonator is possible only if the input wave has a optical frequency close to one of the resonance frequency of the resonator. So, in resonance, the contribution of the input wave leaking through the input mirror adds constructively to the circulating the wave, and there is a destructive interference for the reflected field. The input field reflected at a input mirror is cancelled by the field leaking out of the resonator. So, there is effectively no reflection in the resonance. The contribution of the light wave leaking through the input mirror adds constructively to the circulating wave. So, we can get there is effectively no reflection in the resonance, and in anti-resonance the circulating field is quite weak and the most radiation is reflected at a input mirror. So, the weak field leaking out of the resonator towards the input source adds constructively to the reflected field, and this frequency dependent transmittance is an example where we assume that all the incident light is mode match to the fundamental spatial resonator mode. You can see on the screen that the frequency dependent transmission of the linear fabricated with the mirror reflectivities of 90%. All the constructive we are taking in between that. So, here we can get the high gain as compared to the. So, the resonance frequency can often be tuned by changing the cavity length with a piezo actuators, means we can change the mirror distance, just forget the resonance frequency to tune. So, when the voltage applied to the piezo is periodically varied, so the position of the mirrors is changed. So, with a triangular temporal shape, and the transmitted power versus time is monitored with a photodetector and or an oscilloscope. The latter can directly display the optical spectrum of the incident light provided that the spectral width is smaller than the free spectral range and scan is slow enough to reach the quasi-stationary state of the resonator. So, we can plot a graph through time versus frequency, so that we can get the compare with the resonant frequency. Another is a ring resonator. So, the ring resonator features a closed loop configuration we are having, enabling the light to circulate in a circular path. As it is a ring resonator, so light will move in a ring. So, you can see we can see a diagram that light is moving inside in the form of the ring resonator, depicting the continuous wave input as a resonance. So, the optical ring, the ring operator find the application in the integrated optics, filter and optical switching as well as the non-linear optics for frequency conversion and parametric processes. So, the ring resonator features a closed loop configuration enabling light to circulate in a circular path. So, the ring design allows for minimal losses due to the absence of sharp corners and the possibility of achieving the higher Q factor compared to the resonator type. In the optical ring resonator, a set of waveguides in which at least one is closed loop coupled to some sort of the light input and the output. So, but they are not limited to being waveguide. The concepts behind optical ring resonator are the same as those behind the whispering galleries, except that they use light and obey the properties behind the constructive interference and the total internal reflection. So, whisper galleries use the total internal reflection and the constructive interference. When the light of the resonant wavelength is passed through the loop, as we are talking about the ring, so we are talking about the loop as a light of resonant wavelength is passed through the loop from the input waveguide, the light builds up in intensity over the multiple round trips owing to the constructive interference. It is only because of the constructive interference we have the multiple trips just form the constructive interference and is output to the output bus waveguide, which serve as a detector waveguide, because only a select a few wavelengths will be at a resonance within the loop. So, the optical ring resonator functions as a filter. Only we select a few wavelength, so we use it as a filter. We can filter the wavelength, we can take the one wavelength out from this. Additionally, as implied earlier, two or more ring wavelengths can be coupled to each other to form an add drop optical filter. So, this ring type of structure, ring type of resonator we use for the resonant, we use for the filter. So, ring resonator depicting the continuous wave ring, input as a resonator. What is the working principle? Optical ring resonator work on the principle behind the total internal reflection, constructive interference and optical coupling. So, in the total internal reflection, the light travelling through the waveguide in an optical ring resonator remains within the guide due to the ray optics phenomena known as the total internal reflection, as you all know, that is also used in the optical fiber. And TIR is an optical phenomena that occurs when a ray of light strikes the boundaries of the medium and fails to reflect through the medium. So, at a given angle of the incidence is larger than the critical angle, the refraction index is lower on the other side of the boundary relative to the incident ray. So, TIR will occur and no light will be able to pass through. For an optical ring resonator to work well, total internal reflection conditions must be met and the light travelling through the waveguide must not be allowed to escape by any means. So, another point is the interference, as we require the constructive interference. So, interference is the process by which the two waves superimpose to form the resultant wave or the greater or the less amplitude. So, interference usually refer to the interaction of the two distinct waves, and it is results in the linearity of the Maxwell equation, as you can have the constructive interference. So, in the constructive interference, the two waves have the same phase, and as a result, interference wave that resulting the wave amplitude will be the equal to the sum of the two individual amplitude. So, in the optical resonator, multiple completes multiple circuit round and the ring component, it will be interfere with the other light still in a loop, as such assuming that there is no losses in the system, such as those due to absorption or imperfect coupling, and the resonance condition is met, the intensity of the light emitted from the ring resonator will be equal to the intensity of the light fed into the system. So, without loss we can get the light output. So, you can see on the screen, this is the output coupling, input and output, and it will move throughout the in a round shape, and it will move and it will go out. So, important for understanding how an optical ring resonator works is the concept of how the linear waveguides are coupled to the ring waveguides. So, you are seeing here input as a ring waveguide is here, coupling region, and then output we will get, we are getting without the loss. When a beam of the light passes through a waveguide as shown in the graph ring, part of the light will be coupled into the optical ring resonator. So hence this is the field which extend outside of the waveguide mode in an exponentially decreasing radially profile. So in other words, if the ring and the waveguide are brought closely together, if the ring and the waveguide are brought closely together, some light from the waveguide can coupled into the ring. It is coming in a waveform and it is in the ring, then it is coupled in the ring. There are the three aspects that affect the optical coupling. First, the distance, second is the coupling length, and third is the refractive indices between the waveguide and the optical ring resonator. So, in order to optimize the coupling, it is usually the case to narrow the distance between the ring resonator and the waveguide. So, the closer the distance, the easier the optical coupling happening. So, in addition, the coupling length affects the coupling as well. The coupling length represents the effective curve length of the ring resonator for the coupling phenomena to happen with the waveguide. So, in the ring resonator, wide range of application we are having in the photonics, in the telecommunications and in the other field, in which we use the optical fibers, optical filterings. In the optical fibers we are using in the optical filtering, in the sensing purposes, in the modulation, non-linear optics and the quantum computing. So, they can act as narrow band filter in the optical communication system. It is a narrow band filter in the optical communication system. So, that light can pass through this narrow band filters. So, optical modulators, sensors for the various parameters and the components in the quantum computing system we can use. So, this is used in the it is used in the optical filtering like wavelength division multiplexing and optical add drop multiplexing. A ring resonator can be used to select the filter and the specific wavelength of the light. Moreover, it is used as a notch filter. At the resonance, they can completely block light at a specific wavelength, making them useful as in notch filters. We are using in the optical modulation by altering the resonant wavelength, the intensity of the transmitted light can be modulated and useful for the optical data transmission. In the sensing, how can use? We can use as a chemical, temperature, pressure or biological sensing system we can use. They can detect the changes in the refractive index of the surrounding mediums, enabling various sensing application. In the biosensing, we can use for depositing target particles on the resonator, changing its spectral responses, can be used to detect the presence of the molecules, useful for diagnostic and the food safety application. So, there are the many more application of the ring resonator. Another is a non-linear optics, frequency doubling and entangled photon generation. Nowadays, superposition and entanglement we are using in the quantum computing. So, nowadays this ring resonators, ring type of resonators are used in the quantum computing. The intensity of the light of the resonator can induce nonlinear effect, enabling frequencies doubling and generation of the entangled photon. So, these type of ring resonators are used. As we know that in the quantum computing we require the superposition, as we require the entanglement. So, these type of resonators generally used in the quantum computing system, and as we require the narrow bandwidth. So, they are having a vast number of application in the quantum computing. Now, we will in the next lecture we will discuss the another type of the resonator. So, thank you very much.